we should be able to solve problems. Let's start then. Let's check the symbols. The stream settings. What about the stream title? So, the first problem. Let's solve some problems. I think I haven't solved this problem. Yeah. I've been solving this problem for quite, so I think. Yeah. So So let's start by reading the program first. Yeah. So this is how we are approaching our today's program. So what we are saying is given an array of integers, return the smallest size such that the sum of minus 1, right? So this is a problem that we are given. So let's try to ask what will do we need. So the first thing that I'll ask is constraints on in, right? So constraints on the first question, then constraints on each numbers. For example, all positive or negative. So the second case that I will ask is the input sorted? Because if he gave me an already sorted input, so it will be a nice thing to answer. So, and also, what am I writing, right? I writing a function. So these are the first things that I would ask. So for this, at least estimate 1e5. Then let's estimate if the all positive solution is easy. So let's have negative elements. So for this, the answer is no. This is yes, you will be given the function definition, right? So what about the third type? So let's try to go through an example. For example, let's try to go through this one. So given name saying k, so k is 1. This is the output 1. It is because if we take the subarray of between 1 and 1, it will add up to 1, and its size is 1, right? So let's go through the subarray of, let's go through this example. So I think, so let's go through subarrays. Let's go through each subarray and their size and also their sum, right? So for the first one, what we can go is, we can go with 1 1, its size is 1, and also its sum is 1. 1 2, its size is 2, and its sum is 3. The other subarray, the other notable subarray is this one. The size is 1, and also the sum is 2. So from this, we can see that all of them are less than or equal to k. So we cannot take none, right? So what is the other thing? What is the other thing that we can improve on this? That we can see from this. So the other thing that we can see is this one, for example, in which for L is 1 and R is 3, we can see that sum of L to R is 3, which is greater than or equal to 3, and the answer will be 3, right? So if we go through these examples, I think this will be enough. So I'll try to come up with more examples. So yeah, the first thing that we can see is if it was all positive. So let's try to list our ideas. The first idea that we can have is we can try to calculate the prefix sum. I think the first idea is I have an of n cube solution, which is, it will just do for I in range of n. Then after that, for j in range of n to n, and after that, here what we can do is for k in range of I and j. So we can just increment the running sum by alk, and in this case, after calculating that, if the R sum is greater than or equal to k, we can just try to update the answer, right? So you can just try to update the answer. So we have to first initialize the running sum to be 0. This is a pretty trivial of n cube solution. So the second one is like, let's consider on cases, right? For example, so we can easily optimize this thing into the of n squared time and of one space, right? We can definitely optimize the time and the space, which is we'll try to do for this part, we'll try to store the prefix sums of the array, and after doing that, we can just do the prefix at to get the sum between I and j. We can easily say the running sum is the prefix sum between I plus j plus 1 minus the prefix of I. So this is also another small optimization that you can see. So, but now let's make an assumption, right? Let's make an assumption, right? So what if all the numbers were positive? So this is the first question that I want to ask. So what if all the numbers were positive? So if all numbers were positive, the first thing that we can do is we can do a normal trivial two pointers, because what will happen is if they are always positive, if we try to see the prefix sum of I, for example, if we try to see the relationship between the prefix sum of I and the prefix sum of I plus 1, it will be always increasing. So what will happen is if we find a prefix that is greater than, if you find some array, for example, let's take 2, 1, and 2 in this case. Let's take a to be 2, 2, then 1. Let's take nums to be this array. Let's take the numbers to be this array, and let's also take k to be 3, right? So we can take these two, and if we take this, we can just see that the prefix sum at this point it will be 2, at this point it will be 4, at this point it will be 5, right? So what this will allow us to do is, if we come and reach out here, for example, let's assume we are checking like from left to right? So first we take this part. Let's say we have a pointer at here. Let's denote that here. So first we take this part. Then on the next round we will take this part. But when we are checking this part, we can see that like at this point the prefix sum have become 4. So should we take, so continuing with this element, it doesn't help us no more. It doesn't improve anything. It will make our life worse for us, because the sums will be larger than 3 if we include this element. So what we will try to do is we will try to discard this element, right? So when discarding this element, we will try to, like, let's assume like we are removing it from our window, right? So now it became 2. So 2 is good. We can just continue. So what this shows us is, if the numbers were all positive, we can just write a simple two-pointer, so that we can have a simple greedy solution. So what we'll try to do is, while the current running sum is greater than k, we can just remove the prefix. First we'll try to add the element. After we'll try to add the element, but first we'll try to do this, right? Then if the running sum is greater than k, we have to remove some prefix, right? We have to like shift to the right. So assume my pointer were first here. Then what I did is if the size became greater than 3, so I shifted it to the left. So this is what I did on the first time, right? But if we have a negative element, it will not definitely work because the movement will never work on negative elements. It is like what will happen is, for example, let's take this part. Let's take 2, -1 and 2, right? And let's take 2, -1, 2. So what is the other element? Yeah, but like if we take this and if our running sum, if we want it to be something like what is the value, what is a good value, right? So what is a good example? Something like, let's have something like this. Let's have something like this. So let's have something like this. And let's say our k to be something like 2. Yeah, 2. So here we have 1. So it's working. Nice. Let's go to the second element. Now our running sum become 0. Oh wow. So let's go to here. Now what does happen is our running sum became 3. Our running sum became 4 at this point. So we'll try to remove this so it was like this first. So but we'll remove the first 2 elements. So let me remove them. So we remove the first 2 elements. Now we have 4. So the size is 1, right? So we answered it pretty easily. Wow, amazing. So now let's try to answer another case, right? So let me go to this part and let me go here and let me try to add something like this. 1, 1, 1, multiple ones. So I think let's have something like -100 and 2, right? So here what happens is we were we started with here with 1, then we'll move to 100, it became 99, then we'll move to the next one, it became 97, so we'll move to this one, it became 96, 95, 94, 93, right? So it will never become greater than k. So in that case we cannot remove any prefix. So if we cannot remove any prefix, we cannot tell in of one time, even of n times by using this thing, right? But we definitely know we have to remove some prefix, right? But which prefix should we remove? So that's the question that we have to answer. So from this part, what we have learned is we have to remove some prefix, right? But which one? So which prefix should we remove? So the first, like the best prefix to remove is remove the minimal prefix first. That will be my first constraint. Then also remove the near to end prefix, which is if you have 2 options to remove. For example, let's say if you have here -1 and if you have here -100. So we have first, it will be better if you remove the more negative rather than minimal, the more negative or useless prefix, right? You should remove the useless prefix. We can definitely know that we might need to remove some prefix, right? So But after that, we should remove like the element that is nearest to the current value. So how can we do it, right? I would say let's maintain some data structure like a min heap, which is a priority queue. So if you use that, we can definitely solve it, right? So we can definitely solve it using a priority queue. So what we'll try to do is we will have a running sum which will first be initialized by 0. Then for each elements what we can do is we can just add to the running sum the element, right? Then we also need to maintain something like some heap. So after that, what we can do is we can just try to take some things from the heap, right? So we have to remove some prefixes from the heap. We already have some prefixes. For example, let's see on this one. So on the first iteration, we will add -100 as zeros. So on the second iteration, what will happen is when -1 came, what will happen if I remove this prefix, right? I have -1 and also -100. So I did -1 -100, right? -1 -100, it will become -1 plus 100. Then after that, it became 99. So it is still greater than 2, right? We should better remove it. Because if we try to remove that, if we are not removing that value, we will never get a good result from it. For example, let me explain what I'm saying, right? Here I have -100, right? Here the prefix sum is, here the current running sum is -101. So let's try to subtract -101 from -100. Let's subtract 100 from -101. It will become -1. But it is still less than 2, right? So should we maintain it? Yeah, we should continue. We can't top now. So the second one, so when we are appending to the heap, the minimum value will be up first. So it will be -1, 1, 1. So then for the next case, in this case, the prefix sum now becomes from -101, we have to decrement 2, right? So what it will be the prefix sum? 99. So now let's try to take the first element and compare it with 99. So what is 99 minus, what's 99 plus 101? It will be 2, right? So it's at least greater than or equal to 2. So what I'm saying is, if I remove these 2 elements, I can guarantee that I can get a subset, a subarray that will sum up to k, at least k. So in that case, we can remove some prefix. So now let's try to see how can we do it, right? So while can remove, I think we should better do something like hip hop, right? We should better do something like hip hop from this heap, and also after doing that hip hop, we can heap push the running sum in the index to the heap. So after it, we can return the answer. here the updating connection will be answer will be the minimum is the answer and the current element minus the past. So we can just solve this like this, but still this is not optimal because each call to the heap functions they will individually take of n multiplied by log n time. So that's still something we can optimize. That is still something that we can optimize. So let's see what we can do. Let's see what we can do for it. Okay. So let me create something new around here and let me come here, right? So what we have, let's take something from here, right? So we already have this thing, right? How should we improve from it? Because we are checking each prefixes. We are not even increasing any prefix, right? So, but what if I design some data structure? Let's call it a stack. So, what will this stack do? This stack will maintain things in some order, some predefined order. In this case, we need to just simply pop the minimum element, right? So what should happen is, whenever we find a minimum element, it should say that first. So if we are not finding a minimum element, so whenever we find a minimum element, we should be able to pop it in a time, right? We should be able to pop it easily. So what can we do? We can maintain it. We can maintain. It's not technically a stack. It will be a queue, right? A queue, right? We can maintain a queue, and we can maintain it in a good order, such that it will be like somewhat like this: 2, 3, 4, 5, right? So as we have all these elements, we are introducing an element 1, right? So what is the good thing about 1? 1 is the minimum element, right? So at some point 1 comes, and should we maintain 1 or should we maintain the others? Which one is the better option? So maintaining the others is not as useful as 1. So what we can do is we can just erase them so after that insertion this will happen, right? So 1 will become in our stack. 1 will be the only element in our stack. So for that case, we will try to use monotonic queue and we will try to solve it in orthonic one. So can I go to the implementation part? Yeah, right. So I think so. If we see this thing, we can definitely implement it easily. So I'm going to use Python, and also let me enable my extension by formula. So where is my vim? Let's say tab size 7 spaces, word wrap 2, key binding. I think I need some kind of font ligatures, and let's use Ubuntu Mono. Let's use vim spacing. Yeah, this is beautiful. So let me try to zoom in a little bit, and what we are given is we are given an array, nums and k. So what should maintain, right? We should maintain a window which will be a doubly indented queue, and also let me see something from here, and also we need to maintain an answer. Which in first let's call it a floating infinity. So what you can do is at the end when we are returning the answer is not the floating infinity. Otherwise we should return -1, right? Because since we haven't found anything. So inside, what should we do? We should maintain another running sum, which is, let's call it the running sum, and let's initialize it to be 0. Then for each index and element in the enumerated names, what we can do is we can add the element to the running sum. So what should we do now? Right? So we'll try to do this thing while we have an element on the window, and also the first element on the window we have a running sum, right? This running sum minus the first element on the window, it has to be at least k. So what we will have is the previous sum and the previous index. We will have this, and we can take it from the key, the window, and we can just do a pop left. We can remove the first element since it's maintained in a monotonically increasing order. We can just take the first element. After doing that, so what we can do is we can try to update the answer, right? The answer will be the minimum of the answer, and the p index is the last index that has been removed. So it will be the index minus the p index, right? So now let's add it to our data structure, right? So what you can do is while we have the window, and also the window at the back is at least greater than this running sum, we should remove this element. We don't really need this element. So now we'll do that. After doing that, what you can do is you can just append it, right? We have done all the things that we need to do. So we have to append it, the running sum in the index. Yeah, this is the entire solution to the code. So let's hope it works. We have some cases in this case. So now what we haven't considered is, so assume you have reached at the end, right? So you have reached at the end, right? So but the case was you could have removed an index with 0 elements, right? You can't, because like you could have removed it. That's the easier thing to do, right? So yeah. Let's try to do some debugging now. So, yeah, I think I've seen where my issue is. Yeah, I've seen where my issue is. What? It's crashed. It's just crashed. It's just crashed. What? Really? At this moment? So, where should we be here? Create a new division. Then after doing that, to the window, we can append underneath 0 and -1. Right? Because since they are all zero indexed, if you haven't added this thing, it will affect the rest of them. So you should be able to remove a zero-sized prefix from the array. What we are printing here? We are printing something here. So yeah, this is how we can do it with here is how we can do it with using a queue, a double-ended queue. The second solution is you can use a heap. So let's try to also implement that just for fun. And we can also have an answer to be the float infinity. And how to also have it? We can also have the running sum to be 0. So what you can check is if the answer is the float infinity, we should return -1, right? Otherwise, we should be returning the answer. Now let's do the main part for index and element in enumerate nums. So the first function that we should consider is removing nothing, right? So that's what we should do. We should push this to the heap, right? Because we might not be removing anything, we might be taking the entire element. But after that, we can just increase the running sum. So after increasing the running sum, what can we do is what can we do about it is we can say while we have an element on the heap and also the heap at the first element, which will be at the first element, what we will have is we will have the biggest element. We'll have the smallest element since it's a min heap, right? So while the running sum is that element on the heap, if it's at least k, what should we do is we should store the previous sum and the previous index, right? So we have to say we have to pop it from the heap. So after that, in this case, what we will do is we will update the answer to be the minimum possible, in which the index minus the previous index, right? So after that, we can just simply say index, right? This is just adding the element into the heap. So yeah, as we can see, we got unaccepted. Yay, we got the AC. Yay, try. So definition time. We are grinding. Just